In this video, I'm going to be showing you how I designed and 3D printed a 114mm Newtonian, because I figured how hard could it possibly be? Silly me. But I'll go through the design aspect. It's not what I would call a traditional Newtonian. I've done away with the secondary mirror, but we'll get into that later. So have a watch, let me know what you think in the comments.
First thing to do, jump on eBay, grab myself a cheap spherical mirror, $50, delivered to me door. They did come with a secondary too, but I'm doing away with that. Just simply for the ease of the design element. Second step was to jump onto tinkercad.com and design the actual parts for the scope. Now this took me at least probably 6 hours in total, with a lot of different iterations of bits and pieces. And as you can see here, there was a lot of prototyping and test printing to figure out what exactly I needed to do. And the next thing to do is to stick them on the Bambu Lab printer and 3D print all the parts. So I've got two mid supports, the mirror end, the mirror cradle, and the camera end. Quick trip down to Bunno's to get some screws and nuts and bolts and bits and pieces and some 12mm aluminium solid rod in metre lengths. I needed 4 of. So using M6 by 20mm machine screws, machine bolts with nuts. You drop the nuts into the 3D printed slots to hold each bar and thread a machine screw into it. The bars slide in and then you tighten against them. And that's basically how the 3D printed supports are going to be held onto the aluminium rods. Next part is the mirror and mirror cradle assembly. So basically what I'm doing here is M8 by 45 machine screws through the face of the mirror cradle. And then onto the back of those screws, there's 1/2-inch springs that are, I think they're about 25-30mm long. That will slip through the back 3D printed mirror support. And then these M8 nuts, they're through nuts, so you basically screw them onto the ends of the bolts and they'll allow you to tension the springs to adjust the mirror for collimation. And by doing it this way, it gives us 3 pivot points. So every time you adjust one of the M8 through nuts on the back, it obviously pulls the mirror at one point closer. So you've got 3 points of contact, which means we can adjust it the same as you would any other primary mirror. This part can be a little bit tricky, just getting everything to line up and hold the springs and nuts and screws and everything in place. But I'll eventually get there. Each of the 3D printed supports also have a tab printed into them, so everything aligns just to make sure all the support holes for the rods and that sort of thing are all lined up perfectly. And now for the more delicate part of the operation. So temporarily I'm using heavy duty double-sided tape to hold the mirror in place. Eventually, once I get it all set up and working correctly and everything's where it should be, I'll obviously use some silicone or some adhesive to glue the mirror into place so there's less chance of it falling off. But in this case, I'm just using heavy duty double-sided tape, 3 spots in line with each of the screws to hold the mirror, and basically just lining the mirror up by eye, roughly, to get it in place. Now, installing the mirror, I generally just eyeballed this, but I will eventually 3D print some shims to place around the edges so that as you drop it on, it'll locate the mirror so it's perfectly centered. But even doing this by eye, actually did a pretty good job. This soft tissue paper that the mirror came wrapped in to gently put pressure down on it to get it to adhere onto the double-sided tape. But obviously don't push too hard, you don't want to crack the mirror. Now it's just a case of feeding the aluminium rods through all the parts and tightening the machine screws down with an Allen key to basically get everything lined up. Obviously, try and be as delicate as you can when you get to the mirror end. You don't want to crack or break the mirror or put grubby fingerprints all over it. It's a nightmare to keep them clean. You'll see here the two middle supports. I've also designed them so that they can be attached or bolted onto a dovetail, like a Vixen style dovetail, so the scope can be mounted onto any standard mount. Here's the completed scope. I haven't fitted the dovetail yet. I did have to do another Bono strip and go and get some 1/4 inch by 35mm nuts and bolts to hold that into place. So here's the first basic test. I did put a laser collimator in it and got it roughly aligned. And I've got the SV Bonnie 305C camera mounted into the front of it. You'll see that little blue tab is a shim that I printed so it holds the camera in place. But basically what we're looking at is that tower off in the distance. It's a TV and phone tower. You can just see it in the middle of the trees there. Yeah, so here's looking along the scope. Zoom in into the middle of the trees. This is late afternoon. The sun's still setting across everything, but yeah, here's the sharp capture of the tower itself. So you can see the dishes and everything mounted onto the tower, playing around with the colour and exposure and that. I don't have any shrouds or anything in place, so it's a fully open scope. The mirror's open to sunlight and things like that, so the contrast isn't fantastic, but I'm hoping once I tweak the shrouds, it should get a lot better. Considering a first test run, it's actually not too bad with a very quick collimation. This is the next morning, pointed up at the moon while it's still in the sky. I've had a bit more of a chance to fiddle around with the focus and things like that. I am sort of in the middle of redesigning the front end to make it easier to focus, because if you have a look, there is no secondary mirror. The camera sits at the front of the scope. So forgive me for how crude this looks, but this is a sharp capture, and the moon is bouncing all over the place. The Star Adventurer GDI mount that it's sitting on isn't actually hooked up and powered. This is just me moving it around by hand, trying to line it up just to see what sort of contrast I'd have when I was looking at the moon. So it's not bad for a crudely designed 3D printed telescope in the middle of the day with no light shrouds. Once I get the focuser to be more precise, I'm hoping I should be able to get a lot sharper images. And once the shrouds, I've designed and printed the 3D shrouds of a night time, obviously, we're going to get a lot more contrast. So it can only get better from here. So here's the night of the 9th of April, and I'm going to test it out on Jupiter and just see what sort of image I can get. Now, this scope is at native focal length. It's 114 millimeter by 900 millimeter focal length, so that makes it an f8. This is me playing around with a few things, shooting Jupiter, doing a quick collimation.
Well, that was a relatively successful test on Jupiter, and it's only 7:20. So the moon comes up tonight. I think it should be in the sky about 10:30, 11 o'clock. So I'm getting eaten alive by mozzies. I'm going to pack this up. I'll leave the mount out here, take the scope inside, and I'll come back out a little bit later and see if we can get some images of the moon over night time.
So here's the sharp capture of Jupiter with the SV Bonnie SV305C Pro camera. The color on this thing doesn't look fantastic, but you can fix that in post editing. But you can see here I've got it cropped in. I've got the frame rate up to 99 something frames a second. But this is still at native focal length of 900 millimeters. So the detail on it isn't actually too bad. There's no Barlows or anything in use. And I tried to run the ADC analysis just to see how far the atmospheric dispersions needs to be corrected with this scope. And as you can see, at native focal, it's actually pretty good. They're both within 2 arc seconds, or sort of 1 to 1.5. Obviously with a Barlow it's going to get a lot worse, so you will need an ADC. And then I tried some Planetary stacking. So just have a look and tell me what you think. So here's the sharp capture after it's been run through PIP to stabilise it. Not a super amount of detail, and the colour's wrong, but that's to do with the camera, the Bayer pattern. But you'll see here, after it's been stacked, it's relatively good, and then I put it through Registacks to sharpen the wavelets.
So it's now 1:30 in the AM, and I've woken up and come back outside and set the scope back up to have a look at the moon. And I've got to be honest, for such a little basic 3D printed cheap scope, the Lunar results are fairly spectacular, as you'll see.
It was a little bit hazy while I was filming this, but it doesn't seem to affect the final imaging on the moon. So this is in sharp cap. I'm just getting everything set up, finding the moon, changing the exposure and all that sort of thing so we can see it clearly and centering it. And then, as you can see, it was Actually quite surprising how good it looked. You can clearly make out the crater's surface detail. The contrast is pretty good. So I took some video snaps, some recordings, and I'll stack them and you can have a look. So as I said, this thing's what's known as a Prime Focus Newtonian. There's no secondary mirror. The camera's just mounted in the spider vane at the front. It's a 114mm mirror at 900mm focal length, which makes it an f8. So fairly slow as far as Newtonians are concerned. But I've uploaded, if you go to DomAstro.space and go into the free members area, I have uploaded the files if you want to have a go at downloading and printing and making your own. There's also the parts list there. So yeah, thanks for watching. Let me know what you think, and if you've got any ideas on how to make the scope better, then certainly send them to me in the comments below. But in the meantime, if you could like, share it, subscribe, that'd be much appreciated. Thanks for watching.